Yes, my name is Bjoern Kampa. I'm the head of the Systems Neurophysiology Department at the RWTH University in Aachen. And our main research focus is on the mouse visual system, where we investigate how neurons in the cortex process visual information. So for this, we use, among other techniques, in vivo to photon imaging and in behaving animals. And that requires that the system that we use is flexible enough so that we can adjust it to our behavior setup and that we can fix a mouse that is running in a virtual reality or whatever experiment we do, and so that we actually can accommodate the system to our needs and not the other way around. So in the past we have built our own microscopes for that, and which allows us to gives us the flexibility to actually adjust it to our needs. However, the disadvantage of custom built setups is that they need a lot of maintenance, and they are not always very user friendly, especially if you work with new PhD students who have to learn how to run this machine. For this, it's very important to also have a user friendly platform that you can use for that. And but that still offers the flexibility that you can build your own tools on that and adjust it to the experiment that you run. The important points here are the flexibility that I mentioned, but also in order to have the possibility to look deep into the cortex, to have 3D scanning, to have the possibility for a large field of view, for a mesoscopic access, since the visual cortex actually is quite large with different areas and also surrounding areas that we actually looking at, and to do this, it's a requirement also for us to have different scanners, so resonance scanners and galvo scanners that we can switch in between, and also to that the entire system holds large enough optics so that we can have a large field of view. All of these things are trivial, but not necessarily trivial to use with every microscope. And that was in the past the reason why we had to build this ourselves, also to adjust it to the part of the brain that we actually want to look at and the angle of observation and so on. And for this, it's important to really make use of this technique to have a versatile and adjustable microscope. So one challenge was that usual microscope scans in 2D, but the cortex is a three-dimensional structure. So already during my postdoc in Fritjof Heimchen's group, we extended this scanning to a 3D volume with different techniques. So nowadays we actually use a resonance scanner together with a 3D piezo that moves the objective. And although there might be also other possibilities to achieve that. The other point was that we improved the speed of the scanning, and for this I have used AOD scanners before and random access scan, although nowadays I focus again on the galvo and resonance scanners, which have the big advantage that you can actually see an image or see the volume, and that allows you to correct for motion artifacts, because that's the next caveat. If you work in a behaving mouse, stuff is moving, and so you have to be able to correct for these motion artifacts. Yeah, so my history is more in patch clamp and in brain slices, and recently I went back to this approach using human cortical slices or slice cultures. And this gives us the advantage that we can express GCAMP or other fluorescent proteins, but also opsins in these human slices, and use the same techniques, as I mentioned, that I usually used also in vivo in the mouse. But now we can use this in human tissue. And we can combine this with patch clamp recording. So for this we use multiple simultaneous recordings in order to get pairs of neurons and to investigate the wiring of these neurons. And there the challenge, of course, is first of all to manage to get multiple electrodes into this tissue underneath a small objective. So that is not that trivial, but then in addition, it's also not that easy to perform these patch clamp recordings. And it also requires that you have to change the electrodes eventually, because at least usually it was only one access or one attempt per electrode. And having the possibility to clean the electrode and reuse the same electrode actually has been kind of a dream since my PhD, where I don't know how many electrodes I wasted in order to get the data to just be able to clean it and reuse the same electrode again. That is definitely a big advantage for these recordings as well. So the adjustments we can do on these, or the extensions that we can do on these microscopes are of course unlimited. So the next thing that we want to work on is holographic stimulation, so that we can stimulate multiple individual neurons at the same time at certain temporal patterns. So this has been developed over the last maybe 10 years, and which is also something that we would like to adjust now to our experiments and to our microscope. I think these all optical techniques, they offer a lot of advantages and possibilities. And also the standard measurements that we have used so far was calcium imaging. And I think that voltage imaging also would offer advantages, but also require new technical approaches. You need a faster scanning or a different way of measuring the signal. And the combination of different opsins and different imaging methods is ongoing. And so it's an ongoing development. And so I think there it's important that you can keep up with the field and keep up with these new possibilities to actually include that in your studies. It's a very good point. We train animals, so this is actually one thing that we try to automate to reduce the variability across experiments, so that we have the same task, the same procedure every time. But also for the recordings, the patch clamp recordings, for example, so far this depends very much on the skills and the training of the individual person doing these recordings, and the experience, so that you recognize which is a good neuron, which is a bad neuron, which one is the one that I actually want from all these many neurons that are available. And to have a possibility to automate that, or to at least give you a kind of educated advice, that would definitely be a very big help or big advantage for this approach. Especially because it's not always a senior postdoc who does the experiments. You also, in my case, there are a lot of PhD, but also master and even bachelor students doing these experiments. And they would be of great help to guide those and use technical guidance there to achieve these experiments.